Okay, hopefully the theory lecture didn't confuse you too much. Hopefully this will make it all sort of come together. So today we'll be looking at the Diels-Alder reaction once again, but we'll be looking at more concrete examples of applying the theory that we actually talked about last time. So, say we have, once again, a diene and a dienophile, and you want to do a Diels-Alder reaction on these two. Okay, so let's try to come up with a simpler way of organizing all the theory together and helping you actually do this reaction. So step one is identify which one of your molecules is the diene and which one of your molecules is the dienophile. Well, the diene is going to have two double bonds, so that's this and this. It is also going to have an electron donating group. What does an electron donating group look like? Well, it looks sort of like this. So this is an amine. It has a lone pair. It's able to donate that lone pair onto here. The dienophile is only going to have, well, I'm not going to say it's only going to have one double bond, but it should have an electron withdrawing group. So that's an example. That would be a carbonyl compound. So once you know that, you have both your diene and your dienophile. Some special side notes about this step is that you need to have the correct conformation of the diene. So the diene must be in something called an S-cis conformation. What that means is that these double bonds are lined up like this. So if the second set of double bond is in this direction like this, that would be what is called S-trans. So the S stands for sigma. It is cis with regards to the sigma bond, right? So this is the sigma bond here. The double bonds are on the same side of the sigma bond. Okay, so you need an S-cis conformation, which we have here, and either the diene needs to have an electron donating group or the dienophile needs to have an electron withdrawing group. We talked about this last time. You need this for the energetics to work out and the bonding orbitals to be, well, the orbitals that are involved in the bond to be close enough in energy for the reaction to actually happen. Okay, so suppose that worked out so far. What is step two? Step two deals with the regioselectivity of the Diels-Alder reaction. So you need to make sure that the charges in the Diels-Alder reaction are lined up correctly. Just going to move this up. Okay, never mind. I guess I won't be moving that up. So you need the charges in the Diels-Alder reaction to be lined up. We talked a little bit about what that meant last time, but say you have your diene like this. If you imagine that you push these electrons into here, that'll move these, and that'll move this to here. So what you'll get eventually is a lone pair of electrons located at this carbon here, at that location. So this, we'll say, has one of the charges, sorry, that should say delta minus, because we move the electrons onto there. And in the other location, on the dienophile, you will have the delta plus. So this should be A plus. And that comes from doing the same exact thing. If you move this over here, you could then move this up here. What you're left with is a positive charge on this carbon right over here. So you need to make sure that these two are adjacent to each other for your final product. So let's line them up. That's going to look like this. So if we simply rotate it around this molecule so that the partial minus is here and the partial plus is here. So when we combine them together, these two carbons will be adjacent to each other. Okay. Step 3 of the Diels-Alder reaction. Make sure to position the electron withdrawing groups so that they'll be endo in the final product. So this is the part where it gets a little bit arbitrary, and you got to go along with a convention. So what we mean by that is that you want to have the electron withdrawing groups facing to the right. So on the dienophile, this EWG over here needs to be facing rightward. In the previous step, it was facing leftward. Make sure that is both facing rightward and the positive charge here is still lined up with the negative charge located over here. So just to summarize what I just said, by convention of the dienophile, you want to have, well, in the final product, groups facing right will be endo. That's why you want to put this on the right, and groups facing left will be exo. And when you draw the final product, which is step 4, which is simply to number the carbons involved in the Diels-Alder reaction. So we're just going to go like this, 1, 2, 3, 4, 5, 6, and we're simply going to have the arrows move around in this cyclic fashion. In your final product, when you draw it out, what this is saying up here is that whatever is attached at the 1 and 4 position, you're going to put on a dash. And the electron withdrawing group, you're also going to put on a dash, which is why it's facing to the right. If there was a second group here, coming off here, that would be on a wedge. So this is the endo product. Because this convention over here, that this is on a dash and this is on a dash, is arbitrary, you could also have the enantiomer, which is going to be a wedge and a wedge. Okay? So, with that in mind, I'm going to give you the first Diels-Alder reaction that you should try on your own. So, pause the video and give this a shot. Okay, I'm going to assume that you paused the video. So step 1, identify the diene and the dienophile. So they've already been presented to you, so that's not too bad. Step 2, identify where the partial charges are going to be. Okay, so in the diene, it's going to be located here. Why does that make sense? Well, if you have the lone pair located on this nitrogen, it's going to push like this, and the electrons will be pushed to here. So the partial negative, the del minus, is going to be located on this carbon right here. Similarly, if we do the electron pushing here, this will move upwards, and this will move upwards again, which will leave the partial positive over here. We already have this electron withdrawing group facing to the right, which is fine. So before we draw, we'll number the carbons and draw the arrows. It's going to simply look like that. And then you're going to draw your product, which again is always going to have this diene backbone with the double bond. And we lined up the charges, so this will be lined up with this. That's why we flipped it upside down. That's why this is paired up like this. And like I said, everything that's going to be on the 1 and 4 is going to be a dash. And because we want the endo product, this is also going to be on a dash. The same reason why we made this point to the right. Okay, let's try another one. The only way you get good at these Diels-Alder reactions is you do very, very many of them. Alright, so pause the video and give this one a try. I'm going to assume you give it a try. So first, identify the diene and the dienophile. Ethers are donating groups because, again, they have this lone pair here that can be pushed into the system. Cyano groups are electron withdrawing groups, in part because this N is very electronegative, so this C is going to be very electron deficient. It's going to want to pull electron density away from this over here. Once we know that, we need to draw the partial charges. So again, this one over here comes from the lone pair, donating in, oh, that's a terrible arrow, donating here, pushing this here, pushing the lone pair into this location here, and over here, it's from this movement like this, which is going to leave the positive charge here. So you have the partial negative over here, the partial positive over here. These are lined up. Now you'll notice this is an electron withdrawing group and it's facing left. So what we need to do is we need to orient it so that it is going to be facing right for the endo rule to work. So now, once we have everything lined up, we could simply draw the final product. Again, anything found on 1 and 4 is going to be on a dash. And notice over here, this electron withdrawing group, in consistency with the endo rule, is going to be on a dash, and anything facing left is going to be on a wedge. Alright, so let's see. Give this one a try. I guess I already spoiled which one the diene and dienophile was, but that's not too difficult to come up with. So pause the video and give this reaction a try. Alright, I'm going to assume you tried it. Since we already know the diene and dienophile, the next thing we need to do is identify where the partial charges are. This is going to be pretty close to one of the examples we just did. So we'll push the lone pair to be located on this carbon. Over here, the withdrawing group will move the electrons like this, so you're going to get a partial positive located here. What that means is that we need to rotate our molecules so that the charges line up. And both these groups are facing right. I mean, not much we can do about this, doesn't matter, as long as the electron withdrawing group is facing rightwards. It's going to be endo, it's going to be good. And our product looks like this. Again, 1 and 4. The groups on 1 and 4 are going to be on a dash. Don't draw a dash or a wedge on here. Why? Because it's attached to a double bond, so it doesn't have that kind of stereochemistry. It doesn't make sense to have a wedge or a dash coming off of a double bond, because remember that it is planar. And over here, these are both going to be on the dash, because they're on the same side over here, and they're going to follow the endo rule. Okay, so this one's a little trickier. So pause the video and give this one a try. Okay, first step, identify once again the diene and the dienophile. So this is a little trickier, but the way you can do it is you can say, okay, I know I have 2 double bonds over here, and I also know that alkyl groups are weakly donating groups. So this one's technically got EDGs. Over here, you know that the cyano group is a withdrawing group. So you can say, okay, I know that this has to be my dienophile, and I know that the electron withdrawing group never directly reacts, so I know this has to be the dienophile component that I'm interested in. Because this is a triple bond, we can't make this face right or left, so we don't have to worry about that. As far as charges lining up, we don't really have to worry about that either, because this is symmetric. So we'd simply perform the Diels-Alder mechanism like so. It's going to get a little confusing, but you just got to trust the arrow drawing that you do. So you will have a bond form here and a bond form here. And you're going to have the formation of a double bond on the back of this backbone over here. So if you trust your own arrow drawing, what you'll get is this. So this is the first reaction we've done so far that actually forms a bridge, which is kind of cool. Forgot about that. So you form the bridge over here, and notice that if you trusted your electron drawing, or your arrow drawing over here, this triple bond became a double bond. And don't draw this on a dash or a wedge, because again, it's double bond. You can't have that because it's planar. Okay, let's try another one. Alright, so give this a try. Pause the video and give it a shot. Okay, so this goes back to what I mentioned up here. Actually, I deleted it accidentally. Your diene needs to be in what's called the S-cis conformation. So first of all, let's identify this is our diene, this is our dienophile. Again, this has the withdrawing group. That's why it's the dienophile. This has the 2 double bonds. What you need to do is you need to rotate this bond, the sigma bond over here, to give you the S-cis conformation. So if you rotate this over here, you could imagine it swiveling around, so that's going to be on this side. Then your diene and dienophile will look like this. And at this point, you already know how to handle yourself. Let's make sure that the charges are lined up. Well, this is going to be symmetric over here, and as long as this is on the right-hand side, it's going to be the endo product, so we don't have to worry so much about that. Just number the carbons, push the arrows, and this will be your final product. Again, anything on the 1 and the 4 is going to be on a dash. This could also be located down here. It's symmetric, so it doesn't really matter so much, as long as it's on a dash, because that's going to be the endo product. Okay, another tricky one, so pause the video and give this a shot. Okay, so here, identify your diene and your dienophile. Well, you don't really have that much of a choice. Just make sure that this is in the right formation. You're always going to have this S-cis looking thing over here, and well, this is the best you could do for a dienophile. If you remember from the theory video, this will actually be able to do some secondary bonding in the transition state, so this will be fine in being an electron withdrawing group, or functioning like an electron withdrawing group. Since there's a lot of symmetry here, we don't have to worry so much about lining up the charges. We just simply need to draw the arrows that will be getting our Diels-Alder product. So just trust the arrow drawing that you do. You're always going to get that double bond in the back. You're going to form this bridge head again, and you're always going to get this 6-membered ring. Over here, this double bond is going to remain, and the reason that we need to include these H's on the wedge is to demonstrate that this second ring over here, this 5-membered ring, is endo, that it's being pushed down. So rather than put these on a dash, we'll just put these H's on the wedge, and that'll mean the exact same thing. Okay, switching it up a little bit, how about if I give you the Diels-Alder product, how about you give me the reactants? So pause the video and give this one a try. Okay, so we just need to do the arrow pushing in reverse. So we start here, because we know, well, in the original formation, that an arrow would go from here to here, forming this bond. So in breaking it, we're going to start here and go around like that. If we push the arrows that way, what we'll get is something that looks like this. So the tricky part is the wedge here. Right, so we know that in general this is going to match up with this because these need to be endo to each other, but this is the first time you've seen a difference between a dash and a wedge over here. That means is that rather than looking like this, which you're used to seeing because you've been calling dash dash all the time, you have this group bending up like this, which is irregular. So you know that these are going to be on opposite sides of the final product, but you know that these electron withdrawing groups still need to be endo to this guy pointing outward. So they're all going to be on the same side, and this guy is going to be on the other side. That's the only time you really see something like that happen. Let's see, what is... Okay, yeah. So now try giving me the reactants that form this Diels-Alder product. Okay, so the first step is again, start at this double bond and break everything up. With those arrows, what you'll get is a rather straightforward dienophile, but again, well, you know that over here, these are going to be on opposite sides, so you know that this was formed endo because these H's are on a wedge, so this will be on the right hand side, and you know over here this is going to be on the same side as these, and this will be pointing into, I guess, the diene because it's on the opposite side of the molecule as this. Okay, the last one is sort of bizarre. It's a challenge problem, but was a past exam problem, so pause the video and then give this one a try. Okay, so the way I would start is numbering it and identifying what has to be your diene and your dienophile. And here, instead of having withdrawing groups or donating groups, you instead have strain being your thermodynamic driver. So if you trust yourself to redraw it once you've numbered it, in the typical dienophile fashion, what you'll see is this shape forming over here. And then, once you do the arrow pushing, which looks like this, if you trust your arrow pushing, which is a lot of the Diels-Alder kind of stuff we have to do, you will get the formation of this. And again, And these need to be facing up so that this part of the ring is facing down to demonstrate that it is in fact endo. This double bond also kind of sneaks up on you because you don't expect it, but this is required because it's the backbone of the diene. Alright, hopefully that cleared some things up from the theory video. If you're confident that you understand these practice examples, I suggest going back to the theory video and really understanding why these rules exist and why we sort of